Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, today hopefully we will be done with the first part of the logical agent session. Last time we ended the lecture by defining what we call definite clause and horn clause. And we mentioned that the definite clause is a disjunction of literals of which exactly one is positive. This is like the example here that we have everything that's not positive, but we only have one positive. So this is a definite clause, but this one has two positive literals, so it's not a definite clause. We also defined a more general form of clauses, which is horn clauses. So a horn clause is a clause of which at most one literal is positive. So here it's at most one, which means 0 or 1 positive literals. So it includes or it covers definite clauses, but also has the clauses that has no positive literals at all. So all the definite clauses, of course, are horn clauses, and I think that was the last thing that we discussed last time, that horn clauses are closed under resolution. So if we can apply the resolution on two horn clauses, then the outcome, or what we will infer, will be also a horn clause. Now we'll focus more on definite clauses in which we have just one positive literal, and we will show that every definite clause can be written as an implication. Okay, every definite clause can be written as an implication, and let's see why is that. So here is a definite clause, not A or not B or C. Okay, now this is equivalent to if I group together the negative literals, so that will be not A or not B or C, okay, which is equivalent to, if we look at this, we can apply De Morgan law and we get the not outside the parentheses, so that will be not A and B or C. Now look at this, this is equivalent to A and B implies C. Okay, so every definite clause like this, of course this is an example, any definite clause, since we have only one positive literal, so the one that is positive literal will be eventually the conclusion, and the negation of all negative literals, the conjunction of them, will be the premise, okay, or the condition of the implication statement. So every definite clause can be written as an implication, where the premise is the conjunction of the positive literals, which is the negation of the negative literals that we have in the definite clause, and the conclusion will be the single positive literal. Okay, so not L11 or not breeze or B11 is written as L11 and breeze implies B11. So that's the premise now, and that's the conclusion. Okay, so this is general rule that every definite clause can be written as an implication. Now, what is the benefit of that? The benefit of that is that we can apply a rule like modus ponens. I think you are familiar with modus ponens already. You heard about that from the discrete math course, which seems very useful in this AI course. Modus ponens in general, or the rule that you use to see, is that if we have an implication like that, okay, A implies B, or if A then B, and we know that A is true, then we conclude that B also is true. Okay, now if the premise has a conjunction like that, okay, so if we know that alpha 1 is true and alpha 2 is true up to alpha n is true, then we can infer that beta is true. And this is exactly what we have here. So modus ponens for definite clauses says that if I have an implication like that, and we know that the premise, every literal in the premise is already satisfied. So we have alpha 1 and alpha 2 and alpha 3 and so on, and we have this rule, then beta will be inferred. Okay, so this is like a rule that that we used to see in our daily life. We sometimes we see a rule like, if this happens and this happens and this happens, then that will happen. Okay, now if we know that the condition is satisfied, all the pieces, all the premises in the condition are satisfied, then of course we can infer that the conclusion also is satisfied. This now can be used with the algorithms that we will discuss inshallah today, which are the forward chaining or backward chaining. The idea behind forward chaining or backward chaining is that we have set of rules like this, okay, and we process these rules to activate them and thus deactivate other rules. When can we say that a rule like that will be activated? When the premise is satisfied. So if the premise is satisfied, then this means that this rule is activated. It can be applied now, and we can infer the conclusion. Once the conclusion is inferred, now this is like a fact. We add it to the knowledge base. This can lead to the activation of other rules and so on. Okay, so that's kind of chaining effect. Okay, once we activate something, we infer something from it. Inferring that thing can activate another rule, and so on. Okay, so that's the effect of chaining that will lead us either to prove some given query, or we can just add new facts to the knowledge base. Why is that also important? Because if we have a knowledge base like that, if we have a knowledge base that has definite clauses, which, as we saw in this slide, can be written as implications or rules, then we can apply forward chaining or backward chaining on these rules, and that will run in linear time. Okay, that will be very efficient in linear time. And in addition to that, they are very intuitive to us as humans, because we do that all the time. We keep in mind some rules. Once the conditions of these rules are satisfied, then we keep in mind that the conclusion is satisfied now, and the conclusion now becomes a fact. Okay, and for example, if I have a rule like if today is Sunday and it is 6:30 a.m., then I should wake up. Okay, to prepare for the class, for example. Okay, so things like that. So if the rule is now, if the condition now is satisfied, then the conclusion should be known now, and it will be added to our mind, and it can lead to another conclusion. Okay. We do that all the time. We activate multiple rules. We add from these rules, we add new facts, and we use them to infer even new facts. Any questions so far? So we didn't see yet how forward chaining or backward chaining will work, but this is the idea. Any questions? Everything is clear? Okay. Now forward chaining. In forward chaining algorithm, we have a query that we want to infer, or we can say that it cannot be entailed. Either way, that's same like the resolution and model checking that we explored before. But here we assume that the knowledge base is only including definite clauses, which means that we can convert them into implications or rules, like what we saw in the previous slide. And the idea is that we will activate any rule whose premises are satisfied, add its conclusion to the knowledge base, continue doing that until either the query is satisfied or is found, which means satisfied here, or new rules or no new rules can be activated, in which case that we will say that the knowledge base cannot entail the query. Let's see an example, and then we look at the algorithm together. On the left side here, we have the knowledge base. Okay, so that's the knowledge base. Now, if you look at the knowledge base, all these sentences are written as implication statements or rules. Okay, even these two, okay, are considered definite clauses, right? Because the definite clause is exactly one positive, which is the case here. So all the sentences are definite clauses, and they can be converted into implications like that. Okay, so that's the condition before we apply forward chaining. Okay, now once we have the knowledge base, we can represent it just for for illustration. We represent it by what we call and or graph. So in and or graph, every dot like that is an and or operation. Actually connects symbols by and or operation and indicate an implication statement. So for example, here this one indicates that L and B implies M. Okay, how did we know that it's and? By this arc. This arc indicates that these two symbols are connected by conjunction. Okay, so this one means that L and B implies M, which is this one. Okay, another one, this one. This is L and M implies P. L, and this is the one. L and M implies B. This one is P implies Q. Okay, P implies Q, which is this one, and so on. So this graph connects the symbols together, okay, by and or. Now everything in this graph is and, okay, because we have all the arcs, and actually in forward chaining and backward chaining we will only use ands, but generally the and or graph can also have or, okay, like in this case actually. Okay, so in this case L is connected through two arrows here, which means that P through this arrow, P and A implies L. Also A and B implies L. Okay, so this is like a kind of or here. Okay, so that's why the graph is called and or graph. Okay, and from the knowledge base we can build this graph. Building this graph is not a must for the algorithm. As we will see, the algorithm actually doesn't have this graph, but this is just for illustration, and if you want to solve the problem or the example on paper, that would be good for illustration. Okay, so now from the knowledge base we have this this graph that shows how the rules, how the implication sentences are connected together. Now we are given a query Q, and we want to see if the query can be entailed from this knowledge base or not. Now this is the knowledge base, okay, and we want, using the forward chaining, see whether we can entail Q or not. Now what are these numbers that are attached to the operations, to the dots here? These numbers indicate the number of premises in each of the implication statements. Okay, so for this statement, for example, we have two premises, L and M. That's why we have two here. Okay, and we have two here because we have L and B, and we have two here because we have P and A. and so on. Okay, so initially these counters indicate the number of premises for each rule, and over the time of the algorithm, it will indicate the number of premises for that rule that are not yet satisfied. Okay, that are not yet satisfied. That means that once this counter becomes 0, then we can infer the conclusion of that implication statement. Okay, so this is like keeping track of which rules can be activated next. Okay, right. We keep track of a queue. We call it agenda based on the algorithm that we will see later. The agenda is kind of a queue of symbols that we will process later. Okay, and initially the agenda has all the known facts. So if we look at the knowledge base back, we'll see that A and B are known facts here. So we start the agenda by adding A and B, okay, because they are known facts. So that means that our inference will start, if you look at the graph, bottom up. We go from the facts, and that's natural, right? That's very intuitive. We start from what we know already, and from this we infer other things. So we start with A and B in the queue. Once they are out of the queue, they will be filled. So you see that they are now empty red circles, which means that they are in the queue. Once they are visited or get out of the queue, we will be filled to indicate that they are they should not be now visited again. So we'll get A from the queue now. And once we get a symbol from the queue, that means that it is activated, which means that we should now decrement the counters of the attached implication, in which this symbol was a premise. Okay, so if we go back a step, A now is attached to two implication statements, this one and this one. So once A is activated, then these two numbers will be decremented to be 1. Okay, so if we go now, you see that this is 1 and this is 1, and that's because A was activated. Okay, right. Now A is out of the queue. We should go back to the queue and get the first symbol, which is B now. Now B is attached to this rule and this rule, or this implication, implication. Once B is activated, because it will be out of the queue, we will decrement this one to be 1 and this one will be 0. If you remember, once a rule, the counter of an implication sentence becomes 0, then we should activate its conclusion. Okay, here we will add its conclusion to the queue. So going one step, this one now will be 0, which means that we should add the conclusion of it to the queue. So now L is added to the queue, and this one now becomes 1. Now what we have in the agenda or in the queue is L. We should get it out, activate it. Okay, now it will be filled, and this one will be 0 and this one will be 1. Okay, and once this one is 0, then we should add M to the queue. Okay, so now this one is 0, this one is 1, and M is in the queue. Now M will be out of the queue. Again, it will decrement the counters attached to it, so that one will be 0, and thus P will be added to the queue. Now, once we get P out of the queue, what are the rules that will be affected? This one should be 0 now, and because P also affects this rule, then this one also has to be 0. So if we activate P, now this one is 0 and this one is 0. Now this one, since this one is 0, we should activate L, but L was visited already, so we should not do anything to L. And for this 0, Q will be added to the queue or to the agenda. Okay, now we get okay. So we were here. Okay, now As we said, L is already visited, so we'll do nothing to L. Now Q will be out of the queue, so it will be activated, and we found that it is the query actually that we are checking, so we are done. Okay. So this algorithm will stop in two cases. Either we find the query that we are checking, which means that the knowledge base entails that query, or the queue is empty, which means that we cannot add any more, we cannot activate any more rules, and we cannot add any more facts to the knowledge base, and we can conclude that the knowledge base cannot entail the query. Any questions about this example? Is it clear? Okay, no questions? Good. So here is the pseudocode. You will see that we have two parameters, the knowledge base and Q, and it will return true if we can entail Q and false if we cannot. We have the count here, which is the counter that we saw on the graph. The agenda is the queue that we keep, in which we keep track of the symbols to be activated, and inferred here is the kind of visited variable for each of the symbols. We'll go through the loop, which is getting something out of the queue. So while the queue, which is the agenda, is not empty, once the queue is empty, then we are done. While it's not empty, we get something out of it. And if that's the queue, then we are done. If not, then we see if that was visited before or not. If it is visited before, then we skip it and we get something else from the queue. If not, then we indicate that it is visited, and we decrement the counters that are attached to it. Once one of these counters is 0, then we add its conclusion to the agenda. Okay, and continue. Okay, so we'll get out of this in two cases. In this case, we found Q, or in this case, when we get out of the loop, that means that we didn't find Q and we didn't have anything more to add to the knowledge base, which means that the knowledge base doesn't entail alpha. It doesn't entail Q. This algorithm is both sound and complete, but with the condition that it has definite clauses. Okay, so we call this definite knowledge base. Okay, so the only condition here is that we have the knowledge base is full of definite clauses. Okay, which means that they can be written as implications, which means that we can apply forward chaining. Okay, we'll not go through the proof of being sound and complete here, but I want to emphasize this condition. Okay, so that will be linear, sound, and complete, but with the condition that we have definite knowledge bases. So that's forward chaining. Backward chaining is kind of the opposite idea. So in forward chaining, we start from the known facts, bottom up to the query that we want to prove. In backward chaining, we do the opposite. We start with the query and see what is required to satisfy the query. And this is also very intuitive for us. Give me a second. This is very intuitive for us because we do it actually in many cases in our life. For example, if you know that there is something that has some requirements, for being in graduate school, okay, requires that you get a specific GPA, you get you have to pass a TOEFL exam, for example, and so on. So there are some requirements. So you have a goal, which is getting into the graduate school or the graduate program, and this goal has requirements. So you have to satisfy the requirements. Now you take every requirement and see what you can do to satisfy that requirement, and so on. Okay, so this is this kind of reasoning called goal-based reasoning. Okay, because you start from your goal and going down to the requirements. Once you satisfy the requirements, you activate the goal. Okay, but you recursively consider each of the requirements as a sub goal and satisfy it, and so on. Okay, so this is kind of a recursive algorithm here that defines for your current goal what are the sub goals, and you try to satisfy them. Once you satisfy the sub goals, that means that you satisfy the goal, and so on until you reach the goal that you want, or you cannot satisfy any sub goals. So you can say that the query cannot be entailed. Okay, of course, within the algorithm we have to avoid redundancy. Okay, so we will keep track of what was visited also before, so that we don't go back to it. Here is an example of backward chaining. So here we start, instead of starting with the known facts as we did in forward chaining, we start with the goal. Okay, so we start from the top with the goal. Okay, and we define, or we keep track of a stack of sub goals. Okay, so starting from this queue, okay, we add this symbol now to the stack. Okay, so here we'll keep track of the symbols in a stack instead of a queue, because we do it recursively. So queue now is in the stack, we get it out, and once we get something out from the stack, we put its premises into the stack. Okay, so now queue has just one premise, which is P. So we add it to the stack. Now the stack has only P. We get it out to put its premises, which are L and M. Now we get L from the stack. L has the premises A and P, so we'll add A and P into the stack now. Okay, and we see that P is already was already visited. Okay, and A is known. Okay, so if we check here, so this one and this one are the premises for L, so we add them to the stack, and then, okay, of course P was visited before, so we don't need to process it. Now the next ones to be added to the stack are the premises, and the other rule that L is attached to. So this is A and B. Okay, now A and B are activated because we know that they are known facts. Okay, once we get them out of the stack, that means that we will activate L. Okay, so now L is activated. L is known as a fact. Okay, now M is on the stack. Okay, so M on the stack means that when we get it out of the stack, we will add its sub goals, which are L and B. Now L and B will be considered. Now L and B are known already, so that means that M also will be activated. Okay, so what happens in backward chaining is that we go down from the goal with sub goals, and then once we know facts, we go up again and activate the conclusions. Okay, so now we know that B and L are activated, are satisfied, then M is satisfied. Now L and M are satisfied, B is satisfied. Now B is satisfied, then Q is satisfied. Okay, so we move from up, down, and then going up again when we satisfy the premises, when we know that the premises are satisfied. Okay, so that's backward chaining. Any question about backward chaining? Yes, Faisal? Yes. Actually, no, no. And if you give me a minute just to make sure that no questions from others, I will answer this question, Faisal. Okay. Any other questions? Okay. Now, if you look at forward chaining versus backward chaining, forward chaining is what we call, or a strategy of a type that we call data-driven strategies. Okay. Once we see some evidence or some data, we move from that data to infer something more. Okay. So when we do that, we might do some work that is completely not useful to satisfy the goal or to check the goal. Okay, it might happen that we going bottom up, we might explore parts of the graph that are not useful or helpful to prove the query. Okay, we call that data driven because we start from what we know. We start from the facts, we start from the data, we start from the observations. Okay, so starting from that is called data driven. But backward chaining is goal driven. So we only focus on the things that are needed to satisfy the goal that we have in hand. So we don't do any irrelevant work. We don't do any redundant work. We don't do any redundant work also in forward chaining. But the idea here is that we don't need to explore some rules that will not be useful to us. Okay, so in forward chaining that might happen because we move bottom up, we don't know where the goal is. Okay, but in backward chaining we start from the goal and we put to the stack only the sub goals. Okay, so we know that they are needed. Anything that we add to the stack is actually needed towards proving or disproving the goal. Okay, so we actually do less work in backward chaining. But the complexity of both actually is linear, but backward chaining is actually much less than linear in the size of the knowledge base because there are parts of the knowledge base that are not explored at all, or if they are not needed to prove the query. Okay, Faisal, did I answer your question now? Okay, you're welcome.